Okay, now let's solve. Let's get started with the solving of this question again. Okay, fine. Okay, good, good, good. Let's get started. Let's focus and complete this question here. Y is equal to PQ, PQ, PQ. PQ is my answer. I know my answer. Now I'll get the answer. PQ R S bar plus R S T plus this is R S T plus this R bar S plus R bar S bar plus R bar S T plus R S plus R bar S bar T. Right? Now to take uh, again R bar S bar common here, then this term will go away, and from these two this term has went away, and this RS and RST, this RST will went away, this R bar S and R bar ST, R bar ST will went away, and from these only S bar will remain. S bar will remain, and S bar plus, okay, R bar S from S times R bar S plus RS will give U to S itself. Only S will remain. Okay, and then S plus S bar, it will become 1. Okay, it will become 1. So ultimately it will be PQ into 1. So it will be PQ itself. Okay, so option number A is correct. I don't think you are satisfied with my explanation. So I will be giving you a detailed solution again. I will give you a detailed solution again, and definitely until I'm not sure that you understood. I will not move ahead. Let's take it. Let's take it again. Sorry for the confusion. There will be no confusion. I promise you. We will solve this question. PQ R bar S. PQ R bar S. PQRST. PQRS2 plus PQR bar S. PQR bar S plus PQR bar S bar plus PQR bar S bar plus PQR bar ST plus PQR bar S2 plus PQRS PQRS plus PQR bar S bar T plus PQR bar S bar T. What I did, my first step was taking PQ common. I'm taking PQ common, then you will be getting as here as you will be getting here as R bar S plus R S T plus R bar S plus R bar S bar plus R bar S T plus R S plus R bar S bar T. Okay, let's again solve this. EQ times what I told you. Look for the common terms, whatever you can take common. So what I can see here, there are three terms. There are three terms. This is one term. This is one term. Uh, this is one term. In all these three terms, R bar S is common, right? R bar S. This is R bar S. Q is R S bar. So R S bar. This is R S bar. Okay, this is R S bar. Okay, these two terms I am taking R bar S common from these. Uh, from these two terms, I am taking R bar S bar common. Uh, and then from these two terms, I am taking R S common. So you will get here R S bar and R S times T plus 1 from these two. And R bar is common, taking common from these two, I'm getting 1 plus T, and then I'm taking R bar S bar common, so you will get 1 plus T, right? So 1 plus T will become 1 only in all these three cases. Then you will be getting PQ times R S bar plus RS plus R bar S plus R bar S bar. Again, if you see, you can take R common from these two terms. This will become S bar plus S. Similarly, you can take R bar common from these two terms. It will become S plus S bar. So it will become PQ times S plus S bar will become 1. S plus S bar will become 1. It will become R plus R bar, and R plus R bar will also become 1. So we'll be left with PQ times 1, which will be PQ only. So yeah, option number A was correct. So this is the detailed explanation of all the nitty-gritties that was involved in this question. And moving on the next one, you have the XOR connect. There are 100 XOR gates. 100 is an even number. Okay, 100 is an even number. So we know that for even number of inputs, what will happen if 100 is even? This is an even number, right? So you can actually reduce this circuit for the even number of cases. You can go till level 2 itself. Then also you will get the correct answer. Okay. See, x1 is 1 plus x, 1 XOR x, sorry, it will become x bar, and you will get x XOR x will become 1, right? X XOR x will become 1, and for even number of gates. And if it was odd number of gates, your output will be x bar. For even number of cases, your output will be 1. So 100 is an even number, or your output will be C only. Sorry, your output will be 1. Okay, this is what you will be getting. A bulb in the staircase has two switches, one switch being at ground floor, one other, and the other one is at the first floor. The bulb can be turned on and also can be turned off by any of the switches, irrespective of the state of the other switch. The logic of the switching of the bulb resembles. Okay, this is one question uh, which asks us to design a circuit in terms of logic gates. So Let me call this my building. This is my first floor, and this is my ground floor. So there is bulb in first floor, and there is a bulb in ground floor also. And there are two switches, switch one and switch two. A bulb in the staircase has two switches, one switch being at the ground floor, another one at the first floor. Okay, okay. This is one switch is at the ground floor and another one is at the first floor. So let me call as my switch one being present in the ground floor and switch two is present in the first floor. The bulb can be turned on and also can be turned off by any of the switches. A bulb in the staircase has two switches, one switch being at the ground floor. Okay, bulb is in the staircase. So what we call my bulb is in between the first floor and ground floor. This is the staircase. Okay, fine. So this is my switch one, this is my switch two, and this is my bulb. So if my switch one is on, let's say that this was my initial condition and my bulb was not glowing. Suppose this was my initial condition. I came to my home and both of the switches were closed, which both of the switches were in my off condition, and my bulb was not glowing. Then I come and I on the switch one. Then what will happen? My bulb will glow irrespective of irrespective of the condition of the switch two. I'm just changing from 0 0 to just changing the switch one position. This 1 0 will give you one. Now the bulb can be turned on and also can be turned off by any of the switch position. Now again, if you have this case, this switch one was already on. Switch one was already in the on position. Then I climb the staircase, and if I turn on this switch one again, turn the switch two again, then what will happen? Then what will happen? My bulb will become off, right? Then my bulb will become off, and then if suppose if I come again down, and then not disturbing this case, like this bulb is off case. Now if I come down and then press this S2 again to off condition, then what will happen? This case will be changed, right? This case will change and I will be getting one. So if you see what is the logic is being followed here, this bulb will glow when either of the switch are being one, right? So this is bulb will follow XOR operation. But that's not the end of the question. What what will happen like if this was the case? Okay, I came home and I saw like my suppose my first floor switch was on was suppose first floor switch is pressed. I don't know it is pressed or not. The first floor switch is pressed and switch one was closed. Switch one is off and sorry switch one is off and switch two is on. And I came to my home and saw that the bulb is not glowing. Okay, not bulb is not glowing. I saw this close. Then what I do when I press the switch one, this S2 is not disturbed. I'm in the ground floor only. So then my bulb will start glowing. And then what happened? Then I went to switch from ground floor to first floor. I go, and then I pressed this switch two. Switch two, I saw that it is in on condition. Let me put in off condition. What will happen? This case will get reversed. So I will be getting zero here. And then again, if I came to ground floor, if I came to ground floor, the switch two was off, but I turned it off, and then I came to ground floor, and then I pushed S1 to off condition. Then again this will become one. So if this was the initial condition 0 0, you will be getting bulb following XOR operation. And if this was a condition like if either the switches were in on condition and then also bulb was not glowing. So in this case you will see that bulb will follow XOR operation. So actually uh, For most of the people will say it's only XOR operation, but here you can see that the XOR will also resemble the bulb operation, the logic of switching, right? So bulb can be turned on and turned off by any of the switching, irrespective of the state of other switch, right? The bulb can be turned on and turned off. See, the bulb can be turned on and turned off. This bulb can be turned on and turned off. See, S2 is acting to make bulb on and off. And in these two cases, in this case, you can see S1 is used to turn on and off the bulb. So in this way, you can see both XOR and XNOR will be is the switching logic that is resembled by the bulb. So XOR and XNOR both are option. Both are correct actually. Okay. Let's move on to the next question. This is an MSQ. Output Y is, let's see, A B whole bar, and this is B plus AB whole bar, B times AB whole bar, this is B times B bar plus B bar, which is A bar B. So yeah, I am getting A bar B, and this is C. This is A, sorry, this is A bar B times C whole bar. A bar B times C whole bar. If you expand it, you will get A bar plus B bar plus C, which is A plus B bar plus C bar. Sorry, A plus B bar plus C bar. Yeah, this is what I'm getting. So C and D both are correct. Output Y they are asking, since B bar, this is A, and this whole location will be A XOR B bar. This is nothing but A XOR B whole bar, and this bubble will what will do? It will take a bar of this bar again, and you will get here A XOR B. This is A and this is B bar. So you will getting here A XOR B bar, which is nothing but A XOR B whole bar. And this bubble, what it will do? It will complement the previous input. So it will be A XOR B. Now A XOR B bar, it will event inside this. Let me call it as P, then it will become P bar. So what I am basically doing here, I am doing P XOR P bar, which is nothing but 1. So 1 will get complemented by the output, and output Y will become 0. So C will be my answer. Now A XOR B times B XOR C plus C, which combination of ABC will make Y as 1, right? Let me expand this thing. A B bar plus B bar C. Sorry, this is not the way. You see here, you can write it as A B bar plus A bar B times B C plus B bar C bar times C. Okay. Then we will get A B bar plus A bar B. Let's take C inside this bracket. Then this C and C bar will get cancelled, and we will be left with BC itself. Now again, take BC inside this whole term. Then B and B bar will get cancelled, and we will get A bar BC. Now, if you want this function to become 1, then what you need to do, you have to make A as 0, B as 1, and C as 1. Right? So A is 0, B1, and C1 is a combination of input that will make Y as 1. So this D option will be correct. What is this? Yeah. The shown NAND gate has a finite non-zero delay TD. The circuit act as, if you see, 1 is here, and I don't know whatever my input is. Let me call it as X. So 1 and X, it will become X bar, and X bar plus 1, it will become X, and X will become X, and 1 will become X bar, right? What I mean to say is that if one of the input of the NAND gate is 1, it will behave as inverter itself. So this circuit, no, this circuit is nothing but this way you can see. This is the input, this is my output. This way you can see the circuit. This way you can see the circuit, and this is nothing but a stable multivibrator. It means it will keep on oscillating. This is a square wave or clock signal generator. This kind of output you will get, and this is an A stable multivibrator. Let me again quickly show you how this NAND gate is working as an inverter. Now suppose I don't know what was my output here. I am calling it as X. Then X and 1 and operation will become X, and this bubble that is not operation, that will give you X bar. So this X will become X bar, and this X bar, and there is one X bar and 1 will become X bar, and this dot operation will make it as again X. So what you are seeing here is that this output, whatever the thing which is in this line, in this loop, whatever the thing is there, whatever 0 or 1 is there, this keeps on changing. If it is VDD, it will become 0, then again VDD, then again 0, whatever thing. This kind of output we are going to get here. So this property is I stable multivibrator, means this 0 is also not a stable state of the circuit, 1 is also not stable state of the circuit. If circuit is at 0, it will try to go to 1. If it is as 1, it will go to 0, and this thing will keep on repeating, and it will become a stable multivibrator or square wave signal generator or clock signal generator or ring oscillator that we say. So these all four names are there. Let me quickly write all these names. This will become square wave generator, or it will become ring oscillator. We can also call it as uh, clock signal generator. The classic name A stable multivibrator is already there. A stable multivibrator. So this thing I just remembered, so I'm just telling you. So this A option is correct. B bar C plus AB plus A bar C is equal to, okay, what will it equal to? A B bar plus A B bar. A B plus C bar plus B bar C. Right. If you see here, B and B bar were fine. Great. Okay. There should be something which I can take common here. I'm taking A common here to become B plus C bar, and then here it is B bar C. And then this B plus C bar can be written as B bar C whole bar, right? De Morgan's theorem, and then it will become B bar C. Let B bar C, I'm calling it as T. So it will be B T bar plus, okay, B T bar plus T. Then if you see, it will become B plus T times T bar plus T. So it will be 1 only. So it will be B plus T. And what was T? T was B bar C. B plus B bar C will become B plus B bar into B plus C. B plus B bar will be 1. We will be left with B plus C. I'm sorry, I'm so. Oh, this was A actually, not B. Plus T plus T. B plus B bar. A plus C. Sorry for the confusion. I'm solving it again. Okay, this is A X bar plus X. I'm calling B bar X and X. So it will become A plus X. A plus X. A plus X means A plus B bar C. And if you write it, it will be look like this only: A plus B bar, A plus C. A plus B bar, A plus C, A plus B bar, A plus C. Please. A XOR A bar plus B is equal to A XOR A bar plus B. Okay, first of all, do not apply distributive property in the XOR gates. This is the catch here. So you just expand it as it should be expanded. I'm just expanding it using the XOR property, right? Okay, here what I did, A bar into A bar plus B. This is another one simple kind of observation that I'm telling you. A into A plus B. If this kind of thing is there, you can directly write it as A only. How I am doing so? If you expand it, it will become A plus AB, right? A into A will become A plus AB. To take A common, it will become 1 plus B. So it will become it will again be it will become again we can become A only. So A into A plus B, this will become reduced to A. So similarly, A into A bar plus B will become A bar. So I'm getting as A B bar plus A bar plus A bar plus B bar. This will become A B whole bar, right? See, this is what I'm getting. Assuming that the variables and their complements are available, there's a minimum number of two input NOR gates required to implement XOR gate, right? NOR gate to for two input XOR gate. Anyway, let me show this one. Like if you have, we know this thing, right? The this number of NAND gate to represent XOR operation. So we know that there is four NAND gate required to represent XOR operation, and five NAND gates are required to represent. Yeah, four NAND gate is required to represent XOR operation. Five is required to represent XNOR operation. And if we talk about NOR gate, then four NOR gate will be required to represent XNOR operation, and five NOR gates will be required to represent XOR operation. So question is asking how many two input NOR gate is needed to implement a two input XOR operation. Okay, so answer will be five. If you want, I can show you how to solve each one of these gates. Okay, there are four more questions. Okay, for now let's agree to this thing, and answer is five only. This is a detailed. I will come up with a detailed video for playing with the XOR and XNOR operation with the NAND and NOR gates. This will be fun to watch that video, and you will be getting all the insights there. If I do this now, the video is already too long, and it will be taking yeah, it will take too much time. So I'm sorry for that, but I will definitely come up with to come up with the explanation, like how these four, five, like, and I will also tell you the concept of dual, through which you can convert any of the reducing. There are certain kind of questions, right, where they will be giving you Boolean functions, and they will ask you what is the minimum number of NAND gate or NOR gate that is required to implement that function. So we'll look on those questions as well. So okay, I will come with that. Now move on to the next question. This is an LED, and this is A, B, and this is A, B, and operation, right? And this is B or C. What you will be getting here, this is AB times B plus C, 4 bar. This is AB times B bar, C bar. This B and B bar will cancel out each other. Will give rise to 0 also. This whole term will become 0. If this is 0, right? If this is 0, then if this is 0, then how the LED will go low? Oh, sorry. Sorry, it's not. I think I need to take a break, but definitely I want to end this, then only I will go for my break. So this is AB times B plus C, this whole bar. So this will be AB plus ABC, which in turn will give AB itself. AB itself. This is AB whole bar. This is nothing but NAND gate. Now, if you see, if any of the input is zero, output LED will glow, right? If A is zero, my LED will glow. If B is zero, then also my LED will glow. If A and B both are one, then also my LED, then only my LED will not glow. If A and B both are one, then only my LED will not glow. If any of the input is zero, output will definitely glow, irrespective of C. So possible combination of ABC photon on this option A and B. That is what the answer is. If A XOR B is equal to C, then B bar XOR C. Okay. This is the interchange theorem if you see, if you remember. If A XOR B equal to C, and then if it is asked about B XOR C, then the A will interchange position with C, then yeah, input will become C. And if I apply this bar here, then bar will also come here. So my answer will be A bar. Next thing, A bar plus B. Okay, how many inverters inverting operations are there? One, two, three, four, five. So five NAND gate will become five inverting operation will become corresponding to one inverting operation itself. So this is A XOR B XOR C whole bar, or you can write it as A XOR B XOR C. Okay. Okay. I will explain it a little bit here. Let me solve it in regular method only. There is some certain trick also, but I don't know if you're able to understand that or not. So I will be solving this in this way. First of all, this A XOR B bar is equal to A XOR B whole bar. At least just first agree to this term. Then this whole term here will be A XOR B whole bar, and this there is already a bar above that, complement operation above of that. So these two will cancel out each other. So my operation will become A XOR B XOR C bar, and then again bar. Now this XOR and this bar here and bar above, they will also cancel out each other, and you will get A XOR B XOR C. It is same as A XOR B XOR C. Okay. In fact, this thing you can write it as A XOR B XOR C whole bar, and this bar you can give it to here also. This you can convert this XOR to XOR. So XOR B XOR C, this is the correct answer. The inverter are driven off a supply of 2 volt, and their threshold point are at mid supply. At what point of time V naught T goes to VDD? Okay, V naught T. This is an RC charging and discharging. Hmm. Okay, guys. I need to take a break now. I can solve this, but definitely I need to take a break now, and I will come up with this solution. This solution I will upload, and along with the playing with XOR and XNOR gate, like XOR, sorry, XOR, what is the input combination, and how to reduce, how to know that how many XOR or XNOR will be, how many, sorry, NAND and NOR operation are required to convert a given function to get the function equivalent in terms of NAND and NOR gate. So I'll be coming with those things as well. But for now, let's call it a let's end this video here. I'm running out of time. Thank you. Thank you for